All right, this will be the final video in this video series addressing homework for chapter section 8.1, lines and equations, equations of lines in 2 and 3 space. So let's begin. We left off on question 16. Determine the vector equation of each line. Okay, so each of these problems, it's going to require us knowing one direction vector, and then one point, and the point will become a position vector. So that's what we'll need for this question every single time. One direction vector and one point, which we will use as our position vector. Okay, if we were to not have a direction vector and a point, but instead we have 2 points, then what we would do is we would form a direction vector out of those 2 points using the component-wise subtraction. And then we would take one of those points, if it's A and B, we can take A, and we'll use that as our position vector. Okay? So, now, part A asks us to find a vector equation parallel to the x-axis through P0, 3, -8. Okay, so we can use 3, -8 as our position vector, as we did right here. And then, if it's parallel to the x-axis, we need a direction vector that would be parallel to the x-axis. So I, the vector I, would work perfectly well. So that's why I used 1, 0. You can also envision this as being, you have 3, -8, that's somewhere here, this point P0. The line that would go through it that's parallel to the x-axis looks something like this. Okay? So then the vector equation of the line has to be a direction vector along would be I, right? And we can scale that with t as many times as we like, or in the reverse direction as well. Okay? Good. Moving on to part B. So part B, I have 2 approaches. One is a bit more naive than the other. I did the naive way first, if that makes you feel any better. So it's asking us to find a vector equation perpendicular to 4x minus 3y equals 17 and through the point P0, -2, 4. Okay, so the issue will not be the position vector because we're given that in a sense through the point P0, -2, 4. So the goal is to find a direction vector. Okay, so what I did first is I wrote down the scalar equation as shown. Then I transformed it into its slope-intercept form, y equals mx plus b, like so. That's just isolating for y. And then I can read off the slope, which is 4 over 3, as a direction vector that's 3, 4, right here. And then the perpendicular vector is just, I swap those 2 components and I make the y component negative. So 4, -3. So that becomes my direction vector. And then my vector equation is quite simple, right? I use the position vector, -2, 4, plus t times 4, -3, because that would be the line that has a perpendicular direction vector to the line we're given, 4x minus 3y equals 17. Okay? That's the naive way. You shouldn't do it like that. How you should do it, if you want to be quick, you could do it like this. It doesn't really matter, I guess, but you can recognize that the scalar equation form, ax plus by plus c equals 0, the coefficients in front of x and in front of y correspond directly to the components of the normal vector, 4, -3, right? So then that immediately gives you your direction vector, and you already have your position vector, so then you can immediately jump right to here. Okay? So whatever way you come across it is fine. Mathematicians are usually lazy and we want to do the least work possible. So the latter way is probably preferred. Okay, part C, parallel to the z-axis and through P naught 1, 5, 10. Okay, so same. This question is similar to part A. So the issue is not the position vector, because we're given that through the point we're passing through, 1, 5, 10. It's finding a direction vector. So I used K. And the reason being is we're parallel to the z-axis. So a vector that's parallel to the z-axis is 0, 0, 1, or the vector K. You can envision this same problem in 3 space. So you have 1, 5, 10. Let's say that point is P naught is here. And then the line going through it would be like this. Okay? So that's why this is the direction vector along this line would be K. I can add it any times as I want with the parameter T as well. Okay? Perfect. Part D. Parallel to x, y, z, 3, 3, 0 plus t, 3, negative 5, negative 9 with x-intercept negative 10. So if I need to find a direction vector and a point, right? So the direction vector I'm going to take is going to be parallel to this line, right here. So it has to be parallel to its direction vector, meaning I can choose any scalar multiple of this direction vector in particular. I just chose it to be the same one, okay? And I know it goes through the x-intercept negative 10, so that'll be my position vector, negative 10, 0, 0, right here. And my direction vector is 3, negative 5, negative 9, okay? Because it's parallel to it. So any scalar multiple of 3, negative 5, negative 9 would work, but I just chose exactly that one. So that would just be multiplied by 1. Okay, good. That's question 16 done. Question 16E actually has an error in it, I discovered, so don't do that one. Just go up to 16D. Moving on to the last 2 questions. We have 33 and 34. So I just want to make sure I'm recording. Question 33 asks us, for each symmetric equation, write the vector and scalar equations. Okay, so I did all these in the same kind of format. So first, I wrote down the problem. X minus 6 over 2 equals y minus 9 over 7. The symmetric equation, remember, comes from isolating the parameter t. Right, so these are all, both these sides are equal to t. So step 1, what I did is I cross multiplied. Okay. And then I end up with this right here below. Now, from this, I can actually transition quite easily into the scalar and vector form. So that's what I did, I recognized. So the scalar form is I just move everything over to the left-hand side, make my right-hand side equal to 0, and I'm done. And have it in the form where the x comes first, then the y, followed by the constant. Okay? The vector equation, I can also transition to quite easily. I just isolate for y in this guy. By isolating for y, I get it into its slope-intercept form. So this is slope-intercept form, y equals mx plus b. And the reason I like this form is because now you can easily just read off the vector equation. So the vector equation follows from, you take the y-intercept, negative 12, as your position vector, 0, negative 12. And then you take the slope to be your direction vector, so 2, 7, right here. Perfect. And I pretty much continue this procedure for B and C as well. So I have this, x plus 3 over 4 equals y plus 9 over negative 5, right here. I wrote bad form because you're not supposed to have a negative in the denominator. It should have been moved up in the problem. But it's the author, I guess, didn't really care that much. So again, you cross multiply. Boom, boom. Then you end up with this equation. And from this equation, it's quite simple. You transition you can transition into your scalar or vector forms. To get your scalar form, move everything over to the left-hand side, make your right-hand side equal 0. X first, then y, followed by the constant. So just one thing to recognize is that in the scalar form, you never want to have a negative out front. So right here, there's a negative out front. That's just bad convention. So I factored out a -1, and then I divided by it. So to get 5x plus 4y plus 51 equals 0. Right, like so. Okay? Vector form, same deal. Instead of transitioning to my scalar form, I first go into slope-intercept form again. And then for my slope-intercept form, my y-intercept becomes my position vector, 0, -51/4. And my slope, I can mimic that, and that becomes my new direction vector, 4, -5, right over here from this. Beautiful. Okay, and part C, very similar story. Cross multiply. Cross multiply 4 minus x equals 7y plus 70. The scalar form, move everything over to the left-hand side, make your right-hand side equal 0. First the x term, then the y term, followed by the constant. Make sure it's in good convention to factor out a negative. So factor out a negative if you have to from the front. Okay, that's the scalar form. The vector form, first go into slope-intercept form. First go into slope-intercept form, and then proceed to use your y-intercept as your position vector and your slope as your direction vector. Good. That answers question 33. Question 34. So, in 3 space, the symmetric equations of a line are given by x minus x naught over z over m1, y minus y naught over m2 equals z minus z naught over m3. Where x naught, y naught, z naught is a point on the line, and m1, m2, m3 is a direction vector for the line, provided none of m1, m2, or m3 is 0. Given each vector equation, write the symmetric equations. So that's just following the procedure, right? I'm told how to write it, so I'm just going to copy it. So I'm given the vector equations, the symmetric equations. What I'm doing, essentially, yeah, I'm just copying the procedure. So how can I show this? So x naught, y naught, and z naught are stuff you have to plug in yourself. Those are the components of your position vector. So 1, 3, 9. That becomes 1, 3, 9. Okay? And it's a minus 1, 3, 9. And then the components of your direction vector go in the denominator of each of these fractions, 5, 4, 2. Okay? And same deal for Roman numeral 2. In this case, we have -4, so it's going to be x minus -4, which is the same as x plus 4. Okay? Y plus 1, z minus 7. And then again, I divide by the components of my direction vector for each one respectively. So divide by -2, 8, and then 1. Okay, but again, this is in bad form. Right here, this is bad form. You don't want to have a negative, so I just moved it up. Simplify the numerator like so. -x minus 4. Y plus 1 over 8 equals z minus 7. Okay, good. Question 3 is done in a similar fashion as well. Yeah. So question 3 is not any different. Just making sure you don't have a negative in the denominator. Okay, question 34b asks us, given the symmetric equations, write the corresponding vector equation. So now I do the procedure in reverse. Okay, so x minus 4 divided by 8. I know the x component of my position vector will be 4. The x component of my direction vectors will be 8. Y minus 12 over 5, the y component of my position vector will be 12. And the y component of my direction vector will be 5. Z minus 15 over 2. The z component of my position vector will be 15. And the z component of my position vector will be 15, and the z component of my direction vector will be 2. You follow the same procedure. If it's a positive, right, if you have y plus 1, right, then you're going to have negative 1 here. And yeah, plus 5. Z plus 5 will be negative 5 here. Okay? And then you just divide by it. If it's 7, negative, so it's going to be 1, 7, negative 3, because this is divided by 1, this is divided by 7, and this is divided by negative 3. Okay? So 34b, Roman numeral 3, this question was a bit tricky because usually it's in the form x minus some number or y minus some number, right? So what I first had to do was I had to change it into that form, which I showed you here. So with the arrow, this arrow indicates it. So I factored out a negative from this expression. So it's negative x minus 5 equals, I factored out a negative here as well. And I kept this one the same. And then I can tell what the author probably did was move this negative came from below, right? So I moved it down. Again, bad convention, but I'm assuming what the author was doing. Okay. And then, yeah, then you do it the same way as usual. So you have a x, so you have a 5, y plus 3, that becomes negative 3, 0, there's nothing, this is z plus 0, and then negative 6, negative 10, 11 for our direction vector components. Okay, that concludes the video series for section 8.1. I'll see you all for chapter section 8.2, equations of planes. Thanks everyone, have a good day.